Okay, so the work that I'm going to go over today was done in August last year, the actual field work, and I gave a presentation last year at our FarmLink Open Day, and I've just sort of abridged it and cut it back to just focus on the soil pH aspects of the study. So yeah, I'll kick into it. So hopefully around 20 minutes, 20. So just for any of you guys who don't know, my name's Eva Moffat. I work for FarmLink Research based at Temora in New South Wales. FarmLink's a not-for-profit member-based farming systems group, and I've just grabbed a little screenshot from Google Earth to show our approximate sort of geographical footprint. This slide's pretty loud, but basically I've just grabbed that from the Soil and Landscape Grid of Australia, showing soil pH and calcium chloride in the 5 to 15 centimetre zone, just to show where that dashed area is sort of the footprint of the FarmLink region. So we have a sort of gradation from the east to the west, from quite acidic granitic soils through to sort of transitional, and then out onto the flats, particularly the out towards Urana, and then in the north towards West Wyalong, where we have more alkaline soils. And then within that area, we have a lot of variability of soil type. So what we know is that we have moderate to high levels of within paddock variation in soil physical and chemical properties are pretty common in our region. So it's certainly not uncommon to have, you know, 2 or 3 soil types in the same paddock, and that site-specific amelioration strategies are increasingly important for cost-effective targeted inputs for our increasingly large management areas. So I'm sure similar to other parts of Australia, where, you know, pulling down fences, amalgamating paddocks, and you know, having a site-specific approach to our inputs, particularly our ameliorants, lime and gypsum, that we use in this area, makes economic sense. So what we still need to learn, though, are methods to accurately map or predict pH stratification or subsurface acidity. So this has been an issue that's really only sort of come to head in the last few years, really, or a greater appreciation of it, that our 0 to 10 centimetre soil sampling really isn't picking up on the full story of what's happening in the soil profile with a lot of things, but particularly with pH. And another thing that we really need is an updated acidification model to calculate our lime rates based on our current farming practices. So when the traditional New South Wales DPI liming charts were developed, that was based on work from sort of the 80s and 90s. A lot of it was high rainfall work we were incorporating, so we were cultivating at those times. In those times, we weren't producing as big crops, we weren't adding as many fertilisers, so things have changed substantially, and we're still using the same charts to work out our liming rates. And that chart also only accommodates for a 0 to 10 centimetre soil sample, so it doesn't allow us to, and it's not very user friendly. So if we've got you know, multiple soil tests across the paddock, like a Veris test or a grid soil sample map, then it doesn't do the job for us. We can't easily plug in our rates and plug in our values and get liming rates. So that is actually something that we've recently put an application in through the National Land Care Project Smart Farm Partnerships to work with the DPI to develop a new acidification model. But we won't hear about that for a while, and it is possibly a bit of a long shot, but I think it's a really important thing that we need for our region, for central and southern New South Wales, and I'd say probably across the farming regions of Australia. So this particular study, as I said, we did in August last year, and it was basically like a sort of a pilot or test study. We did it in partnership with Precision Agriculture, who are a sponsor of FarmLink. So they paid for all the soil tests and donated their time as well. And yeah, we went out there and did some pretty intensive soil sampling in a 50-hectare paddock just south of Ardletton. So probably not so important for you guys, the details, but basically you can see the position in the landscape, of the paddock. The main thing to look at is that there's variability within the paddock. So to the north of that sort of creek feature, there's a sort of prime soil, so a red loam that grades to a medium red clay at depth. So getting a higher clay content at depth is pretty common in our area. And then to the south, transitioning sort of to more of a red-brown loam, clay loam. And then in the far south of the paddock, there's actually some gilbite features, which I think some people call them crab holes and have different names around the country. But you can see from the topography there. So there's a decent bit of variation within this paddock. The elevation, there's not a great deal. It's reasonably flat, but basically it drops from the west to the east about 13 metres or so. And the EM38, so the apparent electrical conductivity, really reflects sort of the soil types that we can see and that the farmer sort of knew anyway that we could get from our aerial imagery, but it's nice to put some figures around it. So around that creek feature is sort of the lowest EC readings, and then over those hill highs, we've got the highest readings. So basically what we did, and there's just a picture of the paddock there, so you can see what it looks like on the surface. So what we did is we did a 2 hectare grid pH phosphorus CEC map. So this is a pretty common, I guess, data collection method that growers use in our area, and that's the commercial service that Precision Agriculture provides. So we wanted to have a look at that and see, you know, how well it was actually capturing the variability in pH spatially, so horizontally, but also vertically throughout the profile. So their method is to take 8 individual subsamples over that 2 hectare area and then bulk them together, and that's one soil test that goes to the lab. And within this paddock, so on every second sample, we would like to have done every sample, but it was just basically what budget we had. We also did some segmented deep samples, so down to 100 centimetres in 4 segments, and we did some segmented shallow pH samples, so 5 centimetre segments down to 20 centimetres. And for those tests, we basically did those samples sort of within 25 metres of the GPS point. So for the segmented samples, we used what we call a dig stick. I'm not sure if people have used these before, but their other name is a spur probe. And a fella in, I think, South Australia manufactures them. Basically, it's an open-sided soil sampler that you can bash into the ground with a sledgehammer, and then you can really accurately get those 5 centimetre segmented samples. You can also use pH indicator or barium sulfate to get a visual, so you don't actually have to spend money to send it off to the lab. You can sort of just do it quick and easy and see if you've got pH stratification, or if it looks pretty uniform down the soil profile, then you don't have to waste your money sending them to the lab. And then obviously the hydrolyte is just a day break soil sampler to get the deeper soil samples. So we also had EM38 data, which was actually collected in 2017, and that's sort of how we identified this paddock based on that data. And what I did with that is I did a 5 metre grid inverse distance weighted interpolation, and then I sort of cookie cutted out the 25 metre diameter points, and then I got an average ECA value from each of those points to sort of compare and gauge the correlation between different layers at different depths. So I won't go into too much of the detail about the results, the deep soil results, because we're also really interested in looking at sodicity and dispersive characteristics in this paddock, because the farmer has applied gypsum in the past and had a yield response off it as well. So we were trying to have a sort of a combined lime and gypsum strategy. But I'm just going to focus on the lime today, but just very quickly, those correlations sort of allowed me to just compare the ECA to MIR particle size texture, which, you know, sort of wasn't too bad of a correlation. Basically, as the ECA went up, we had a high clay concentration, which you would expect. The same with salinity or EC or chloride milligrams per kilogram was a tighter correlation, so that was probably mostly driving that ECA in the EM38 survey. Moisture wasn't great, and CEC was pretty good. So all of that sort of made sense and kind of reaffirmed, I guess, our zoning and how we were sort of approaching the paddock. We also saw some nice visual differences in the cores between the different areas. So quite a brighter red sort of chrome sol in the north of the paddock, whereas in the south, around those gilbite features, we had a sort of grayer clay, which again really makes sense. Chrome sol being freer draining, more iron oxides, whereas in your gilbite sort of heavier soils, a bit more waterlogged, and generally going to get a sort of a duller grade soil profile. One interesting thing that I did pull out of the data when I compared the CEC on the deep soil results, which is on the y-axis of this graph. So as you go up the y-axis, it's getting a higher CEC, so generally associated with a heavier soil. And then the clay percentage on the x-axis of this graph from the MIR particle size analysis, we really saw that there was two distinct populations. So in the north and the south of the paddock, which again makes sense because that's driven by different types of clay. So different clay species, for instance, say smectites, which have that shrink swell behaviour, which creates gilguys, are going to have a different CEC, so a higher CEC for the same clay percentage. So yeah, that was just something interesting that we sort of, I guess, allowed us to really zone the paddock in two distinct populations, data populations. So now getting back to the pH. So this is just our 0 to 10 centimetre grid results. So not looking at any of the deep stuff at all, just looking at the 0 to 10 centimetre test. On the left, you can see there is quite a bit of that, the CEC variability is coming through in the 0 to 10 centimetre, which is good. I think that's a useful data layer. I think you combine that with, say, your seeding fuel usage or something like that, you would get a higher resolution data layer, but this gives you some real numbers to work with as far as your CEC. On the right, that's your 0 to 10 centimetre pH and calcium chloride. So looking at that, actually it doesn't look too bad. So we generally, if we were only testing 0 to 10 centimetres and we got that map back, we'd probably say, okay, you could probably apply some lime in the northern half of the paddock. It wouldn't be a terribly high rate, and we think the paddock was in pretty good condition. And then when we looked at the segmented results, so the 0 to 5, 5 to 10, 10 to 15, 15 to 20, sort of told a fairly different story. So in the 0 to 5 centimetre, we've got quite alkaline conditions. I might add, sorry, I forgot to say at the start, that this paddock hasn't had a liming history. There's possibly a tonne to the hectare went out just to the north of the creek many years ago, but basically it hasn't had a lot of lime. So this is a natural process that happens when you're not cultivating, you're not incorporating, you're getting leaf residue, alkaline material accumulate on the surface, and you're going to have a narrow band at the surface that is more alkaline. Then going to the 5 to 10, there's a really dramatic drop. So sort of pushing toward a 2 pH unit drop between those two segments. So the 5 to 10 centimetre, we've got some pretty low values in there. Not terrible, but it would be enough to sort of say, okay, we probably would want to grow a sensitive species like a pulse or barley. We generally think 4.8 is sort of the threshold where we're going to get yield constraints there. So, and pretty surprising considering the 0 to 10 centimetre results to see that in the 5 to 10 centimetre. And then below that, the 10 to 15 centimetre, we've still got some acidic areas, some aren't looking so bad. But the interesting thing to me was that those areas really lined up quite nicely with what our EM38 survey was showing us. So basically saying that where the CEC is lower, so the buffering capacity isn't as great, we've got that acidity dropping deeper into the profile. So that was quite interesting because I thought, okay, so we might not be able to map the whole paddock in 5 centimetre segments, but it's sort of saying that using some other proxy data layers like ECA might be a good way to sort of pick out where you go and take your strategic segmented soil samples, because they are quite expensive. And then, yeah, just lastly, in the 15 to 20 centimetres, most of the paddock is getting more alkaline by that point. So below that, we do see this paddock would actually drop to sort of 6, 7, 8 pH and calcium chloride at depth. So certainly, you know, subsoil sodicity, alkalinity is another issue in this paddock. But as far as acidity, we're really only worried about the sort of top 20 centimetres. So when we have a look at the 0 to 10 centimetre map that I've already showed you on the left there, and then when I calculate 0 to 20 centimetres, so from those segmented ones, basically what we're seeing is that the 0 to 20 centimetre is pretty scary, because not only is that a lower overall pH, it's actually twice as much soil volume. So when we're doing our liming calculations, we're treating twice as much soil. So we go from not needing to apply very much lime at all to all of a sudden, you know, really having a fairly substantial lime application required. So if this is indicative of the rest of our region, then that's pretty alarming in my mind. Another way just to display what I was talking about before around the correlation between the EM38 or the CEC is to graph it up the way I've done here. So basically on the left is your CEC chart of the 0 to 10 centimetres, so only the topsoil. And then on the right, we've got those 5 centimetre segmented pH results. So pH increasing on the y-axis, and then our 4 different depths on the x-axis. And I've colour-coded each of the lines to match the area on the map where it's come from, basically. So the 2 darker blue lines are the ones from the sort of 13 to 17 CEC area, and that's where those gill guys were. So they're pretty good. They're not, you know, they're fairly alkaline, and we wouldn't expect to be lining those zones, and it would be a waste of money to just spread line in those zones. Everything else, well, firstly in the 0 to 5, we notice that it's really jumbled, so it's all over the place what's happening on the topsoil, which I think is fairly common in my experience, or you know, from the results that I've seen. But then when we jump to the 5 to 10 centimetre results, apart from those 2 in the gilgai areas, they're really tightly constrained, still quite jumbled, but all sort of around that 4.5 to 5. So that's really where that acid throttle is occurring, in that 5 to 10 centimetre. And then when we progress a little deeper to the 10 to 15 and the 15 to 20, a pretty cool thing happens. They split out into their CEC groups, basically. So we're seeing the lowest, the lightest soils, the lowest buffering capacity soils, which are red, are the ones that are actually getting more acidic or still quite acidic at 10 to 15 centimetres. Whereas when you step up through to those sort of slightly heavier soils, those ones are getting more alkaline again. So they're the ones that we probably don't need to apply as much additional lime to treat in that subsurface zone. And then just another way to, I guess, visualize that is that using the pH indicator, the top one out of the 4 is the one from the lightest soil zone, and you can see it is the acidity has progressed the deepest in that area, and then as you step down, the acidity hasn't progressed as the acid front, I guess, hasn't progressed as deep right down to the bottom, which is in that gill bar area, which is just alkaline all the way down. So management implications. Our grid soils mapping can be used to gauge the horizontal spatial variability of pH and CEC, which I think was probably even more useful in the topsoil. But we really need to take some deeper segmented tests to see the full picture. So only looking in the topsoil is just, it's not really giving us all the information that we need. So use either the segmented sampling or just the DSIC sort of visual tests within your soil management zones to determine where you've got subsurface acidity happening. Lime to 5.5 pH or higher, which is a bit of a hard pill to swallow, but if we can get that 0 to 10 centimetre at least up to 5.5, we have a chance of some of it moving deeper. So if we only target lower levels, the lime is going to be consumed and neutralised before it really has any effect on the subsurface. So we need to try and push higher in the topsoil. Apply additional lime over soil zones where subsurface acidity is detected. In this particular example, I actually did two separate calculations, one for the 0 to 10, one for the 10 to 20. It just depends how much detail you want to go into, I guess, when you go to make your variable rate lime map, and what sort of tools that you might have to support those calculations. And lastly, lime needs to be incorporated to react throughout the soil profile, or injected, or in some way to be in contact with the acidic soil. So in a high pH environment, as if when you just spread it at the surface and it's not incorporated, lime is really insoluble. So it's basically immobile. It's just going to sit there and it's not going to react. So unfortunately, at this time, although we don't like cultivating our soil, that is really the only practical thing that we can do to make sure that that liming effect gets down into the profile. On quite a lighter sandy soil and with a high enough rate and high enough rainfall zone, it might get down there eventually, but most of our soils in this region sort of being clay loam sort of in the topsoil, really we're looking at incorporation. So then the conversation becomes about being strategic about when we do that. So whether that's if we're bringing a pasture out and we need to work the soil anyway, or if we could somehow do that over spring rather than over summer when we've still got some soil moisture, and maybe get something growing there and spray it out to hold the soil together, because the last thing we want to see is lots of worked paddocks flying away over summer. So what's next? The Gilgai paddock that we mapped. We did variable rate lime injection maps. We developed those with the grower, and they were applied over the summer just gone and incorporated. So we certainly at a similar time of the year, we'll go back and do some follow-up testing to see how effective those applications were, and see where we're at. And then the other thing, we were really lucky to get some funding through the National Land Care Project's Smart Farm Small Grants, which were announced back in April to undertake a larger regional study over this coming summer. We've got budget to test about 2,700 hectares using a similar-ish method, not quite as intensive as the one that I've just outlined to you. So that'll be sort of 15 to 20 growers within our region. And hopefully we can see if these trends are, how universal they are across our region, and if those management approaches that I've outlined, hold for different soil types, different rainfalls, different management practices, and paddock histories. So yeah, that's basically it for now. And I have written that report up in our annual research report, which I will dig out and put on the Google Drive, I guess, if anyone wants to chase up any more details. That's all.